This is a lab also. I would like us to be interactive. We need to talk a little bit more because we will be doing things together. When I mean things, like trying to code together, test out some things. So, great. This is okay for you. Fantastic. Let's get to it. Welcome back, everyone. We are now in the lab session. If your friends are not here yet, I recommend you reach out to them via your different channels so that they can join the lab session. This is an extension of my talk this morning. It's still on nonlinear modeling, generalization, regularization. The dataset we are using is the specified dataset that I mentioned. Is everyone in the lab notebook? Do you have access to the lab notebook? Are you able to click on that link in chat and see, can you see this notebook that I'm sharing right now? Okay, so the first thing, thanks a lot, Sarah. The first thing we should do, first of all, is to click on this link here so that we can download the data. Do we all have the data now? Click on the link. The dataset is hosted on Kaggle, and you can just download it. You have to sign in on Kaggle. If you already have a Kaggle account, if you don't, you can quickly sign up. Should be easy. If you have downloaded this data, can you write in chat that you have the data set downloaded on your device? Are we still downloading it? Okay, Sarah, thanks. Any other person? Maybe 2, 3 more feedback and then we can proceed. Obi, thank you. Waiting for 2 more. Okay, Samuel, making 3 people. Fantastic. Thanks, Damilola. This is good. Time talk with Jack. Okay, we all have downloaded it. It's sitting on your computer. The next thing is that let's upload it. Maybe some of you use the Kaggle API, which is great. Whatever works well for you, you should use it. So once you download it, you need to load the data set into your Colab directory. So I already have the data set here, right? But how would you do that? You just click on this button and then you upload it. Should be okay, right? Do you all have it on your Colab now? You've uploaded it to your Colab workspace. I need like 5 people to tell me that they have. Have you uploaded the data set into your Colab space? Okay, thank you, Sarah. You have 1. 4 more people should please confirm. Okay, thanks, it's your top. I hope that is the right way to pronounce your name. So we need 3 more people to confirm that they've uploaded this data. Samuel, thank you. Waiting. Me, okay. Hobie, thanks. One more. Just one more person. It's okay. We'll wait for you. Once you have it, Okay, great, Jack. Great, great. You have it, everyone. So about 6 people has it now. So let's keep going. We can proceed now. So first thing first, let's load in our library. So we will be using pandas, NumPy, and this is for the data analysis vectorization library, and this is for visualization. And you can also run this. It's just that the NumPy a global parameter for some of the plot to make the plot figure look like this slide. So it's all right. Yeah. This is why it's eating, but just wanted to show you in case you're curious. So coming to the data set, the first thing first, let's load it. We're using pandas. We read in the dataset that we have just downloaded. Whatever you called it is what you should write there. So if you did not call it Nigeria specified songs, then you need to change this part of my notebook. I hope that you have created a new copy of my notebook so that you can run along. Can 3 people let me know if they already run this cell? And you can see all of this. Okay, damn, a lot of things for the feedback. All right, I think Sam also has. All right, great. For your convenience, I also provided what each of the features means, but you can just go to the Spotify link. I put some reference down below to read more about it. One of the references is just where you've been. It also has a short explanation of what each feature means. And you can, if you still don't understand, you can go to the Spotify web API, which I linked below. So yeah, I linked it below the Spotify web API. Maybe it's useful to click on it since we are on the call. Let me just quickly. I didn't think ahead of time. I would have put it somewhere I could find it easily. Okay, yeah, this is it. Yeah. So if you click on this Spotify web API, you can see that it has different, Spotify has different API. Again, I must say they're very strict about the usage of the data. I didn't download this data from here, you know that, because we just saw it on the cargo dataset. But irrespective, it may be that this is not allowed according to their like user license. So, you have to tread carefully. What is the name of the dataset on cargo? So it is called Nigerian Songs Spotify. You can, if you search for it, I think you should be able to find it. All right, great. And here you can see all of the audio features, right? If you go to track and get track audio feature, you can see the different audio feature, and there is even an example of what value it can take in the documentation that Spotify has so brilliantly put together. So this is just, if you're curious about anything you don't understand, for example, I didn't really, when I looked at this, I did not understand what time signature was. And, when I read about it and Googled more to learn about it, I was like, I see. So now I kind of like have a vague idea of what it means in this context, right? Okay, that is the Spotify web API. Let's quickly scroll back. Sorry for the scrolling. So we now move slowly through the tutorial. Okay, so if you run this cell here, there's something I wanted to show you, which I think I found interesting, is that first of all, it will list all of the, it's like you want everything, right? It lists all of the row, 530 rows and 16 columns. But if you scroll all the way here, there are two things here. I think maybe it's a new, like, Collab just added it, or maybe they've added it a while ago, but irrespective, I just noticed it. And if you click on this suggest charts button, it will just create a bunch of figures, a different configuration of the data set. So, for example, you can see the distribution of the release dates. You see that we have a lot of, like a few data that is between 2000 and 2005. And most of the data that we have is from, say, 2010 to 2020. You can keep going. You can keep going to the side. I think there is more. There should be more plots. Okay, yes. So this is another plot. The length, which is in milliseconds, like how long this song is. We have song that like maybe less than 2 minutes to song that are up to maybe 8 minutes or something like that. But you can see that most of the songs are not so long. The distribution is fairly normal here, and it's centered in this 200,000 milliseconds, maybe 2 minutes, or like I'm not sure. I have to compute it. And the popularity column, you see that it's very spread out, right? But there are a lot of songs that seems like they are not popular in this data set, and then there are like some songs that are like very popular. The higher the better. Danceability is skewed to the right. Most of the songs seems like they are danceable. And if you just keep going, you can quickly just have like a very quick understanding of like the data set that you're working with, the release date versus the length of the song. It seems like as we increase the release date, like these days, most of the songs are not so long, but we still have some outlier here. This kind of like look like a non-linear relationship, right? Anyway, so yeah, this is just for you to just have a feel of the data set that we're working with, and what can we use to predict, like what kind of task can we do with this data set, and like how should we go about it, right? So in for this notebook, what I have done was to look at the loudness and the energy column, like I mentioned earlier this morning in class. So this energy and the loudness column, because I find that a lot of the columns are not correlated in a non-linear way, so to say, like in an interesting non-linear way with popularity. So at first, when I got this data set, I wanted to predict the popularity, but the popularity column was not the relationship between the column and a lot of these features was not very pronounced. So I thought it's not as easy to use it to explain the concept of nonlinear. So I chose the energy and loudness, even though like from what we talked about this morning, it seems like the relationship between energy and loudness is more linear than nonlinear. So it's not that long. It's not like very non-linear, where you can clearly see it's fairly linear. Like as you increase the energy, the loudness increases, which is something you would expect, because it's an attribute. Energy is the measure of like high energy, high loudness. Anyway, So in this notebook, we will talk about the relationship between the two features, loudness, energy, where we're trying to predict loudness from energy. So I'll show you the code. So we just run through the code together. This is the purpose, because we already talked about it this morning. And then we will look at using more than one features to do the same prediction. And I hope that by the end of the tutorial, you can also try out some more things, like what does the performance look like when you use other feature, maybe even the popularity, or even like when you try to augment this Spotify data with other data source, like what can be a good predictor of how popular a song would be. I mean, in my mind, it's like there are some artists, no matter what they put out there, people end up like, it's like it becomes popular at some point. Like, so it's not just about the song, but also the artist's popularity, I think, may have something to do with the song popularity. Maybe not so much. Maybe there's just something about the song that is popular that makes it popular, and the features, we can find more features to augment this. Any comments so far before we keep going? Okay. Looks like there is nothing to add. So let's run this cell here. So we just have a data frame that only consists of energy and loudness, and we can see link to the Colab. All right, I'll reshare it. Just a second, sorry. So this is the link. Let's come back to it. So when we do this, we can plot this, and then we have this relationship. And the first thing I did was to try to approximate this using a linear model. And how did I do this? I talked about X transpose X, X transpose Y in class, which I said was the solution to the parameter theta. So now we are just going to use the linear algebra solver to solve this problem. If you run, you're getting an error. What error do you get? Which cell gives you an error, Jack? Which cell? Does anyone else get an error?
Where this code, which is under nonlinear modeling?
This one gives you an error.
Yeah, that one.
What error is it showing?
That the name songs df is not defined.
Then maybe you forgot to run this this one here. You have to run this first. Okay. Did you run this cell?
It's okay. I can just run it. You can just proceed.
Yeah, okay. So run this cell. This would load the data set into songs DF. Once you run that cell, then you can run this cell and it should work. You should now see these plots. And so now that we have the plot, we can write the linear equation, right? So again, what we just have here is the same thing as when we had theta. We had theta equals to X transpose X, right? Then X transpose. By the way, this is called I'm using LaTeX to write this equation. It's okay if you don't know what that is. I know it because it's very important to know as a researcher. Otherwise, you cannot write, a researcher in computer science, you cannot write paper easily. So, so X transpose X inverse, then X, it's X transpose Y, is it? No, yeah, it's X transpose Y, right? This was the formula. Remember this formula, right? Guys, I need feedback. Do you remember the formula that we talked about in class? That is, we said it's the solution in here. Thanks, Sarah. So this is the same thing. Now we are just we now want to solve it like linear algebra. There are different ways to solve to solve this to like different ways to solve this problem. But there is a very handy function in NumPy called linear algebra solver. And like that function just it solve any kind of linear, like any system of linear equation that can be written in the form like ax equals to b. As long as you can write it in the form ax equals to b, then you can use linear algebra solver. And so this like if you look at this form, this equation here, you can see that you can write it in this form. So let me tell you the mapping so that you can see it. So in this this theta, if you rewrite this now, x, you can have something like x equals to a inverse b. Can you now see the relationship? So a becomes x transpose x, right? B becomes x transpose y, and x is the theta we are looking for. Great, thank you. And then once you see this relationship, I mean, you can just write it as a, you can just write it, you can just put it inside the linear algebra solver and it will solve it for you. If you're curious about what this solver is, you can just like look at it on sklearn, which is what everyone does when you this is SciPy. I'm looking for, oh no, I said sklearn, NumPy rather. Sorry. You can just look at NumPy. So this is the NumPy linear algebra solver, and it explains to you how to use this this function here. So if you're ever unclear, just maybe go to the documentation or just Google it and find the right explanation for you, because sometimes documentation can be very complete, but if you're just starting out, it just feels like a lot of information that you don't need right now. So we write that, and then we can plot this. Just take this away. You don't need this. This is just to explain this. We can now, once we have the theta, right? We already have the solution. So we just want to plot the solution, what it looks like. And here, this is just saying that you want to, I just take 2 points to be able to plot that line. I need 1 point here and I need another point here. Are you seeing what I'm doing now? So I just chose 0 and 1 as 2 points. And then, so it's like, you just want to predict on 2 example, and you multiply it, like theta 0 is the bias term. Remember, we've been talking about that. And then theta 1, oh, sorry. Yeah. Okay, sorry. Theta, the first one here, this first one is the weight, and the second one is the bias term. And let me show you what theta looks like, so that it's not like I'm doing Ojoro here. You can see it yourself. So when we've not run this, sorry. Let's first run it. Have you run this cell? Has anyone run this cell? Anyone? Did you run this cell already? Maybe 1 or 2 people. Yeah. Okay, thanks, Sammy. So once we run this cell, right? Let's now look at what theta is. So it should be just two value, the weight and the bias. Remember, mx plus b or theta 1 plus theta 0. So b here is the bias. And I'm not lying, because you can always read out the bias from the y-axis. It's also known as the intercept. And you can see that it's like negative 14 something. So this is definitely the bias. And this 12.13 is the weight. Is the weight that that gave us this line in that direction. So if you change this weight, you will get another line. Okay, but right now this is the best kind of weight and bias we can have for this plot according to our solution. You know, we had a system of linear equation and we solved it, and the solver said that the best possible that we can get for this data is this line, right? Is that clear? Is everyone clear on, you know, the mathematics here? Sorry, do you know what this art is doing? No. Okay, great. So the art is called dot product. It's just an easy way to write it. You can, the same thing that we wrote here, you can write it as let's take it out. You can write it as NP the dot. It should be, yeah. You can see that, and now it's a dot product between A and B, and you do A. This is going to be like this. The answer should not change. It should be the same thing. It's because it's a dot product. You can say that it's the same answer. So art is just an easy way to write the dot product. Do you know what dot product is, Samuel? Oh, Sarah, no. Okay. Now this one is another thing. It's just we did makes sense now, Taiwo. All right, thanks. So dot products is, I mean, it's just a way to multiply like a vector, two vectors together. If you want to multiply two matrices together or two vectors together, so inner product is called dot product. And I don't, I'm not saying too much now because we did linear algebra. Like Kenichi went through that part in his class, and I would recommend that you look at it. But just a quick example: if you have two like two vector, let's say 2 and 3. This is the first one, and the second one is say 4 and 5. If I do dot product between these two vector A equals to this, and vector B equals to this, can someone tell me what the dot product A dot B, let's put this inside latex. Can someone tell me what A dot B would be? Is this latexing? Maybe not. Great. So A dot B is 23. And how did we get 23, right? It's 2 times 4, right? Plus what? 3 times 5. 2 times 4 is what? 8. 3 times 5 is what? 15. Dot product, inner product. I just said it's inner product, right? 2 times 4, 3 times 5. This is the dot product between two vectors. But you can also have dot products between a vector and a matrix. So what you need to keep in mind when you start to multiply such is that like if you have, let's say, a matrix here, let's say we have a matrix that is M, like M by N, right? You have a matrix that is M by N, this matrix here, for A, let's say your new A now, it's not the same A above. There's an A that is a matrix, so it's M by N, and you have a B that is a matrix with let's say N times K. If you dot A and B together, what would you get? What is the shape of that matrix that you would get? Does anyone know? I have a matrix of M by N, another matrix of N by K. What will you get? Thank you, Obi. So you will get what? You get M by K. But what happened if what if instead of B being N by K, like you have another B prime that is instead K by N? And can you do A transpose B prime? Is this possible? Is this possible? Or what would you get? Maybe it's possible. So A is M by N and B prime is K by N. What is going to be the shape of the matrix A dot B prime? Does anyone know? Obi, do you think it's also still M by K? What do you think? Anyone? We all don't want to talk. Or is the question not clear? Because this is important, so that you can understand why we do some of the things we're doing. It's not the same shape. Thanks, Gamelia. So this is not it's like the shape is not in a way that you can do this dot multiplication. So you cannot multiply you cannot do this multiplication. Does anyone want to say something?
Yeah, I wanted to say, like, if you are going to do a dot product, the shape of the shape of the column of the first matrix must be equal to the dimension of the rows of the second matrix.
Yes.
So they are not the same thing. So that's why I can't.
Thank you. So this is not possible. But how can we still do this thing? We want to do multiplication. What can we do to make it possible? What do you think? We transpose. Exactly. So what we need to do is that we get this B prime. We transpose it. We do like transpose, and voila, it gives us B. B prime transpose give us B, because then M, like this K times N that we have, once we transpose it, it becomes what? N by K, right? K by N transpose is N by K. And what is N by K? Surprise, surprise, that is B. So now that you have it, then you can now you can do, so the AC dot B is exactly the same thing as A C dot B prime transpose, right? Do you agree? Let's use equivalent. Yeah, right? Exactly. So this is a quite easily solved. I hope this makes sense because you've been seeing a lot of these dot products here. Can you see? So what this is doing right now, when you have an array, let's unpack this. You create an array here. Array. This array x equals, let's say x equals to this, and when you show the output, you get something like this. If you look at the shape of this array, what do you get? 2 by 500, 2 by 530. So it's now like it's like you have two two features, and 530 is the number of sample in your data set. So now it's like you have all of the samples on the column. Like your column is 530 and your rows are 2. But this is not what you want. Usually, you want it to be in this example on the row and features in the column. So what you do is that you transpose it. So once if you transpose it, it looks something like this. See, this is what we are doing here. We transpose it, we change the direction, we just move it like this. And it's still the same thing, 0.42, 0.42, 1, 1, this, and that. And if you look at the shape now, you see that x dot transpose dot shape, you will get 502, 530 and 2. And this is the shape you want this matrix to be in order to solve this problem. So here, like you, as a homework for you, based on all that we've explained, you can see if if this is possible. If it's not possible, there's always an error that will be thrown. A popular error, if you're new to this domain of transposing, let's do this. Let's forget the transpose, and then we try to solve it. You get an error, like it says matrix multiplication. Like this, what we just tried to do is also called matrix multiplication when you're considering two matrices. It says impute operand 1, which is this, right, has a mismatch in its core dimension. Its core dimension with this some signature. It even tells you that n by k should be that this k should be equals to k here, so that you can have n by m, but it looks like this is not the same. Instead of, so you have a different shape, so I cannot multiply things. You need to fix that. So it tries to tell you that there's a problem going on. You need to fix it. So this is it. This is what this looks like. Is this clear? I spent so much time here because I also struggled with it when I started out, because you just see things flying out. You don't even know what T is doing there. You just assume it's all the same. And when you start implementing things yourself, you start running into all of this error that is a little bit painful. So I hope you'll get it now, how the code works. So now coming back, I think, okay, let's take like a short 5 minutes break, so that I can get some water. Is that okay? Would be back like 40. This is 44 now, 49. Is that fine? All right, great. Okay, welcome back. So let's keep going. Here I try to explain. There's hands raised. Please go ahead, Jed. Jed, do you have a comment, question? Or was that a mistake? Okay. We can keep going as Jed tries to figure out. Oh, the link to the attendance form. Okay, let's try to find that. It was shared earlier, but I will reshare it again before we continue. Okay, this is it. Great. It's not a question regarding the content of the class. So the hypothesis function here is the parameter theta1, which is the weight that we talked about, also called parameter of the model, and the feature, which is now we are focused on energy. And this theta here, which is called theta2, that I've been calling theta0 in class, is the so that is the where are we? Yeah, here. So that is the bias, and we can write it in this form, the vector form, to create the polynomial function that we talked about in class, right? And the equation becomes theta1, which is the first this is the weight of the first feature, the first polynomial feature, energy squared, and theta2 will be the weight for the second polynomial feature. And you can continue to have it theta3, theta4, theta5, and if you have more features. So each of the feature has a weight or a parameter that you want to learn. Your learning parameter per feature. Does that make sense to you? Is it good? Is that intuitive?
Yes, it is.
Great. So so now let's try to learn a quadratic function. But before we do that, I wanted to make a note here that usually when you have multiple features, or even one feature that has very high value, you need to try to scale it down because of like floating point issues. So like if you have high order of polynomial, the numbers can get big very fast, which becomes difficult for your computer to represent exactly the number, because it will be over like the range, your double precision for the floating point value. So to help your current hardware, computers, like we've gotten to a great point since when it was invented, but there's still just so much you can fit into the floating point. So we need to scale it down, like scale the feature down so that we can have more room to explore. So one of the ways to scale the feature down is called min-max rescaling or normalization. And as the name suggests, it's that it tries to change your, like, whatever value that like the feature that you give to it, or the color or the vector, it tries to rescale it into to be between the minimum and the maximum that you have specified. A very popular way to do a very popular min max that people do is like minimum being 0, 0, 1 min max, or -1 to +1 range. So here the formula just shows how you draw it. So this is the new value you will get. This is your old value. You subtract the minimum of this your old value. Like here, this is a vector, so it's not a scalar. It's not just you don't just have one element. You have a vector, maybe like 2, 3, or 4. Then the minimum of that vector would be minimum of x, and then you subtract it, and then you divide by the maximum minus minimum. And this new vector that you get here would have a minimum of 0 and a maximum of 1. But in order to generalize this formula to have any like arbitrary range, which a could be like -1 to +1, or maybe -10 to +10, or maybe 2 to 5, any kind of range you want to scale your new vector to. This is a general way to do it, right? You can, if you try this formula yourself, write things down, have like an example, maybe 3 values, so that you can understand things, and then try to do it and see what you get. Then it makes sense. So I already explained this earlier to you about the linear solver, and this code here just does the min max rescaling implementation, where here I implemented it, and I also did the reverse implementation, so that we can go from x to x prime and x prime to x. And here I put a test to show that the implementation works. So if there is no error here, it means that the implementation works. I first min max it, and then I did the inverse min max. So, but this is not very relevant. It's just for knowledge sake, which I think is the purpose of the lab, to learn something new that you don't know before. So have you run this cell? Because you need to run it. I'm calling the min max function that I implemented in the cells below. So make sure you run this. Can I get feedback from 1 or 2 people? Run this cell called min max. Okay, thanks, Damilola. So once we run this, now we need to create the polynomial feature, right? So that we can generate new polynomial feature and fit another model. For example, the quadratic model that we talked about. And to do that, again, we have like a very handy function, but we will unpack this. Here, I'm just giving the user the option of deciding whether or not they want to scale their input. So if you set this to true, it's true by default, but if you set it to false, then it's going to use X without scaling it. But if it is true, then we will scale it. After scaling it, this just creates that polynomial feature that we've been talking about. So let's take this and show, like, let's bring it here. Let's say we have X that is not scaled yet. Oh no, maybe we should even first let's show what min max, I mean, so that it's not just theory and I'm not just saying things. So we had X here, right? And if you do minimum of mean of X and max of X, I just use different notation for different things. You can also do X dot max. So the mean is 0.11 and the max is 0.95. If we do min max scaling, let's scale it. Min max, we just call the function X dot mean, and it will give you x prime, like a new x. This is a lazy coding thing to just show you. So mean max x, if you like write it out, you get another value. It's just like your x, but a different kind of x. Okay, let's call it x prime. So x prime is min max, is this. And then let's look at the minimum for x prime and the maximum from x prime. What do we expect the minimum for x prime to be and the maximum for x prime? By the way, we didn't tell it the range. So the range, the default range that I put there is -1 to 1. So let's just be explicit. Minimum range is this. Maximum range is this. What do we expect, guys? B. What do you think? So if I run this cell, what do you expect that I will get? I mean, you can also run it yourself, see what you got and tell me the answer. Thank you. So -1 and 1, which is exactly what I got. But what if I change this to 3 and 5? Let's see. Does it work? I expect that I will get 3 and 5. Let's run this. So see? So this just help you to rescale to any arbitrary value I want. And if you look at x prime, the values will change, but it's still the same as x, but it has just been rescaled differently, which is pretty cool, right? Anyway, so let's take the x, not the scaled version. I just want to show you what this would give you, in order to create this polynomial feature. It's very simple. Let's say we want to create polynomial feature of degree 2. This is 2, and then we take the x. We just need to square it, and then we keep going. Oh, this is not good. So I mean, I know what it gave, but it's not easy. It's not good in terms of explaining what I wanted to explain. So what I would do is get a small version of x, like x2, so that you can see what happened there. Okay, so we are just focusing on 2 values for now. So when you do this, what do you think would happen? Anyone? What will I get? No, actually 2 is too much. 1. What would happen? What do you think would happen? I'll wait for you to think about it. So we right here, we are using a list comprehension. We did that in week 0 when we did introduction to Python. List comprehension. What we wrote here can be written also as just a regular follow. You say something like output equals to this, and then you say for high in range of degree -1, right? Output dot append high x of 1 y, right? Oh, no, not square, high. So this 3 line of code is this 1 line of code. So it's just like when people sometimes write notebook, like depending on how sophisticated they are as a programmer, they use like the shortcut technique, because why not? Okay, someone said it gives the power of x from 2 to 0. This is true. This is true. So you expect to get 3 values, right? Like now, are we going to get 3 values? 0.42, 0.42 square, and 1. This is what I think we'll get. Do you agree? What do you think, Dolamu? I mean, if I run this line, this cell right now, this one here, what do you think I will get?
You're going to get the power of that, like the value of x. You're going to get the power for
So
0, 1, and 2.
0. So that means we would
1.
have 0.42 to 0 is 1. So 1, 0.42, and 0.42 square.
Yes, sir.
Great. This is correct. This is exactly what we will get. See? So this is raised to 2. I mean, because we are starting from 2, is like 2, 1, 0. How we've constructed the matrix. X square, x1, x0, x raised to power 0. So just generalize this idea, this like from one scalar value to having a vector. This is exactly what we're doing. So now we do the same thing, but now we just have a vector and we transpose it so that we can have the vector be in the form of m by n. So if we run this code here, just put it out here and run it, you will get 3 columns. So now you have 2 features. Before you had 1 feature, right? Just the energy feature. If you remember, before you had, so this is it. Sorry, this is it. You only had this feature. Let's look at X. Let me put it in a way that we can see it like -1, 1, right? -1, 1. Yes, -1, 1. Dot ratio. What is it? It's not so subscriptable. What have I done wrong? Okay, sorry. I see what I've done wrong. Okay, great. So that we can see a few. Okay, see what I'm trying to say. You got 0.4. Yeah, you're right. This is what you got, Lola. So you can see that this is X, right? Remember, X is energy, right? We called energy X. Just so we don't lose track of where we're coming from, I'll use what we had before, some DF of energy, right? I don't want us to get lost in the numbers and forget what we were trying to do. Dot values, which we turn into NumPy. I think this is the same, yeah. So this is the energy column, and I'm just showing only the first 10 rows. There are more rows, there are over 500 rows. I'm just showing the first 10. So you want to create like polynomial features of this energy column, right? This is what we are trying to do. So to do that, we ran this code, and now we would have 2 features now instead of 1. This is the let's look at the first 10 row. So this is the one we had before. Now we have like squared of it, x squared, and this one is just the bias term to make things in a matrix format, which is just to make it easier to multiply things. Instead of doing mx plus b, we can just have like 1 theta x, just 1. So the bias is already included in the matrix for the theta. Okay, is this clear now? So now we've just gone from 1 feature to what? 2 features. Does that make sense? Is it clear to you? Do you understand what I'm trying to say? Thanks, Dolamu. So this is the idea. So once we have that, this is what the polynomial feature does. It's not just for 2 features. In fact, you can do it for a lot of features. Let's go to, why stay with 2? How about 3? See, more feature. 5, you have now that you cannot see things very well. So let's say 4, we have 1, 2, 3, 4 features. If you look at 10, you get 10 of it, and so on. So this is how we are creating this polynomial feature. All right. And then, so once we create this, we already talked about this, right? We talked about this solver. We did it just now, so we know what this is doing. So the least square poly function, this function here, it just does, like, first of all, it tries to get the polynomial feature that we want, which and also, you specify the degree of polynomial. If it is degree 1, it's just a linear function, like linear, just 1. Then if it's degree 2, then polynomial, it becomes quadratic. Degree 3, it becomes cubic, and you can keep going like that. So let's run this cell, and then we come here, we can just run this cell. You can ignore this, it's not necessary. But anyway, the most important thing here is that we use the function that we implemented here, and then this would return the theta. So the theta for polynomial degree 1 is this, and it's quite different from what we had before, right? So when let's quickly come back here. Are you still following me? Are you still following me? Okay, so if we quickly come back to the example before, to the cell before, let's run it again. Let's run this cell again. So I will print out the theta. You see that we got something like this. Remember, I was talking about it before. I was like a 14, minus 14, and the weight is 12. Great, keep that in mind, because I want to show you the effect of scaling. So when we now quickly went down, we rerun things here, and we have a function that already scales the data that we specify, and we now printed out this polynomial, but we kept it to degree 1 just like we had before. And what we see here is that the theta, the weight here, instead of being 12 that we found here, instead of being 12 here, it's now 5.3. Instead of the bias being minus 14, it's now minus 7. So we have scaled things down. The weight is a little bit smaller, and the bias is also it's now it's now -7 instead of -14. But these two are exactly still the same. The effect that they have on the data set is still the same. It's just scaled differently. And to show you what what I'm trying to say is correct, you can look at the minimum for this for this data here, this X here. The minimum value is -1. Remember, this is what we did. The minimum value is -1, and the maximum value is +1. So you can just multiply, just take the minimum value and try to multiply by -1 times 5.3, and then plus it. What I'm doing here is just like mx plus b. So if you do this, b is -7.7, right? And then m is this. And then if you do, and x now is -1, right? If you run this code here, it will give you -12.83. So for the previous data, the minimum value was 0.11. Take the theta, also the same thing, do the same mx plus b. If you run it, you get -12. I mean, there's some precision thing going on here, like 442, 5, 6, 7, 9, and this is just 443. But this and this are the same. Does that make sense? just showing you the effect of scaling. That is still the same solution we arrived at, but it's just scaled differently. Is that clear? Do you understand that? Yes, thanks. Okay, then we can, yeah. I mean, you can go through this based on all the explanation that I've given so far. It should be easy to understand what's going on here. So if you run this function is just to help us plot, like put the plots in a function so that we can easily test things. So when we do this for degree 1, it's the same as we've seen before. So we can keep just realized I wrote polynomial. Polynomial. Oh my God, is that what was on the slide? No, I commented it out. Polynomial. So the second one, so if you do degree 2, you see that now we are fixing the different one. And then these are the things I was showing in class. Degree 3, we have now another one, and you can just keep going. Degree 4, let's see, about degree 5, okay. Degree 10, all right. 50, okay. 100. So now you see that this was when we got to this overfitting level, and then we can now, like, try to think about how to regularize this. And to do the regularization, we talked about the training and test split. But before we get there, let's do another 5 minutes break. Is that okay? Would you like to take another 5 minutes just to stretch a bit? Okay, great. Let's come back 20. All right, great. Okay, welcome back. So now let's move into the train test split that we talked about earlier today, which is just because we need to be able to understand how good our model is on unseen data. So now we've been saying that we said that this model overfitted, but we really don't know. I mean, as far as we can tell, this is the best possible curve that we can have on this data. But because we do know some things about machine learning, and we've heard about overfitting, we quickly realized that this is not the best possible thing to do because it's good for the training data, but we don't care about the training data usually in machine learning. We care about something we've not seen before. So in order to create that scenario where we have something we've not seen before, we need to be able to do like a holdout or test split or validation split in whichever camp you belong. But here we'll talk about, we call it holdouts or test split for now. And the process of doing this is called cross-validation. And the most popular split that people do is the 70-30 split, which is 70% of your entire data goes to the training set, and the 30% goes to the holdout test set. So the simplest way we can do this is just that we need to select some point randomly in our training set and say, oh, all you people, you belong to the train, or the other points you belong to the test. Why is it important to do it randomly? I didn't talk about this in the morning, but it's an interesting thing to think about. Let me show you what I'm asking you. Let's say, for example, we take this and X train X test. I'm going to quickly make this synthetic now so that I can ask you a question about it. Instead of this, I just say first 70, who cares? I don't know if this would, I don't know what I'm doing here, but no, I should think about it. Look for 70. Should be fine, should be the first 70 columns. So the last from 70 downward should be okay. If it's an error, we'll just fix it. Okay, great. Up to 70, X test, Y test, train data, and the test data. This is doing what I'm looking for. Oh, no. Of course. This is so silly. So silly. But it's okay. You get silly sometimes. Okay. What I want is 70% of my train data. What is that? What is 70%? Length of this times so silly. Cannot believe it. But 371. So this is what I want. It just said 70. Okay, this is what I want. So this is one split, right? I look at my training data. I take the first 371 as my train set, and the second 371 in my training data as a test set. Is there anything wrong with this approach, guys? What do you think? It's a split. We take the first 371 and the second 371. Sounds good to me. What do you think about this approach, guys? Can you think of Anything that can go wrong. It's a one-time thing. Yeah. So, like, what do you do again? Like, you only can use 371 data, and you already took the first 371. Like, there's no randomization going on. You can only do it once, and that's it. But if you want to be able to do it multiple times, then maybe you just don't pick the first 371. Like, maybe you want to randomly select this point so that you have like higher chance. You don't get to examine thank you, Dolamu. So you don't get to examine the data properly for validation. So you just took a subset. So another thing that could go wrong is if you have a data collection process that has not been shuffled at all. Like, data comes in a stream, the first data, the second data, the third data, and this is how you collected it in your spreadsheet. If you take the first 371 to train your data, like your next, the rest of the data, like you have no guarantee that you're able to generalize well to whatever it was before, because now you just thought about it like how you would do splitting in the, like, when you have time component, like in the time series. Usually this is the kind of splitting you would do. You would take the first couple of months and validate with the months that comes after. But in general machine learning process that you have like a static data set, like you don't want to do that. You want to learn from everything in your distribution, not like some first 30, like you have no idea what's going on. So it's what you usually do is you randomize the process. The splitting is done randomly so that everyone gets equal chance of being selected to some extent. So this is why what we're trying to do. We are trying to create this randomness so that we get the same results everywhere. Like whoever is running this cell get the same result as I'm going to show now. We put this seed here. This random seed is just to make sure that the result is reproducible. Otherwise, if I don't have the seed, what I get as the subset here will be different from what you get wherever you are, depending on whichever hardware you run it on, because you'll be using different kinds of seeds. So, but if we all fix it, now we can use the same seed to generate this randomness. So and then the next thing is that we use the non-pi permutation, which what it does is just that it gives you a random integer within the range that you have specified, right? So let's get this out. Let's say we want to get permutation of 10. So it gives you 10 data that are random permutation of 10 data, and between 0 and 10, I believe. Yes. So you see that everything here is between 0 and 10, but it's different from if you did np.a range, let's say a range 10. See, you get ordered 0, 1, 2, up to 9. But if you do permutation, you're saying that you want this range, but I want you to permutate it. So every time I run this, I get a different order. Just pay attention. Now the first value is 6. Run it again. The first value is 7. The last one is 9. Run it again. The first value is 2. The last one is 7. If you keep running it, you keep getting different results. But if you want to make sure that you get the same result every time you seed it, run it, you get 815. Run it 1 million times, it will not change. It's the same thing that you always get. So because it's now seeded. Thank you. It shuffles the list properly. This is the right terminology, shuffling. You have a list. This is a list. And you want to be able to shuffle it, how you shuffle cards. And permutation help you shuffle it. So you don't have two joker in the same, like, that follow each other. Shuffling. So it does shuffle. NumPy also has a, like, a, what's it called? A function that is called shuffle, I believe. Okay, so once you have this shuffled list, let's use that word. Thanks to Lamu. Brilliant. So once we have the shuffled list, we can now just select the first 70%. Remember when I did this calculation, this was like 371, right? We do the first 70% and then we put it in the train set. And the last 30%, we put it, as we call it, the index, like IDX, index of the train. This is now the index of the test. So instead of just naively choosing, as we have done here, the first 337, we do a little bit, we be a little bit more, we do it a little bit smartly. So we just put all of the index here. Like NumPy, pandas is pretty cool in the sense that if you specify the different index that you want in this iLog, it just gets you the data with that index. So that's really nice. So we just give it all of the index and it's retrieved the data set that has the index for us. And when we run this, and if we print out our X train, we will get, actually, before we do that, I just want you to see that we have different index. So look at that. So the index that we are choosing is this. You can see that it's like 140. And if you look at X train, you should have 140 as the first one. So 140, 398, 140, 398, 6, 334, 322. So it just retrieved whatever you give it. This is the job. If you print the length of this, you already know that this is like 371 to the train and 159 to the test set. And we can plot this to see what it looks like. We can see that we have different, more like a random selection of the test, and the test's data point and the train data point, unlike here, where a lot of them are like skewed here. Some of them are like here. Okay. Is this clear? Alice clear? Is everything clear? I just spoke German to you. Is everything okay? Thanks, Gamelia. Awesome. Yeah. Wants to write this on my buy check. Yeah. Vielen Dank. So we can move on. So we can move on to the next step, which is to now compute the mean squared error of our model. So we will use this training set that we've just set aside to train a model, and then we use the test set to validate the model, or to compute the mean squared error, so that we can measure the generalization gap. So here I have implemented a function that just does mean squared error, which is just a difference, right, between the predicted target Y value and the true target, and we square all of this error, this difference, and then we get the mean of it across all of the data sets. So run this cell. Have you run this cell? This cell here. If you're here with me at this point, can you put it in chat so I can know how many people are still running? Thank you, Damlola. Fantastic. So, Delamo, thanks. So now what we will do, guys, is that we will try to estimate the error for all of the degree of polynomial from 0, which is a bit silly because 0 is like what? It's the bias term. So, I mean, but we'll leave it there just for conversation's sake. Degree polynomial 0 is just the bias. Polynomial 1 is the linear model, and so on. So this would give you, like, for each iteration, like the first I would be 0, then 1 to up to 100, and we just do the same thing. We compute the train prediction, so we get the polynomial feature, right? The polynomial feature for the train set, the computed parameter. This is the optimal parameter for this particular polynomial 0. The optimal parameter would be what is stored in this variable name called theta, and then you compute, you do theta transpose x, right? This is your x, the polynomial feature now, and then this is your theta. So you can either do something like theta transpose x. If we were writing it in, let's go to somewhere where this can make sense. So we can either have theta transpose x, or we write it as x theta. It's the same thing, as long as the dimension match, like we talked about before. So we are doing the second one, which is x theta, and then we also and this would be our hypothesis function, which is also called prediction, right? So this would be the h theta that we've seen in class. So our h theta is this predicted value. Predicted y is this, what we are predicting. So our train prediction, our test prediction, we compute the mean squared error. Remember, mean squared error is just here, a prediction minus true value. So this will give you one value. This is the error for this particular I. You append it to your list that you've created, initialized up here. You do the same for your test set. You append it, and then you do that n time. Once you have that, you will get a list of how many samples. Does anyone know? What will be the length of this list? Let's see what's following. What will be the length of the list? What will be? Yay. Yes, Gamalian. So it's going to be 100, because we said we want to do it 100 times. So once we do that, we can just run the cell, right? Until we have the training error is going down and the test error is going up. By the way, did you notice that I'm using like log scale? let me remove log scale. If you do plot the plot, right, then this would be non-log. You can see that like it's like this. It's very hard to see. The tested because of this spikiness going on here, which I'll talk about in a moment. But so the log scale help you like see the effect. It makes it much more dramatic if you put it that way. So always pay attention to this Y value because it shows like what you're saying, or like what happened. Yes, please go ahead. Yes, your hand is raised. Is this intentional? Okay, we cannot hear you. If this is not intentional, that's okay. You can come back anytime. So, sorry, it's fine. So you can see here that the train error keeps going down. In fact, let's just look at the train alone for now. So we can see that it keeps going down. Oh, let's be dramatic again. Okay, it still doesn't show well because of this spiky thing going on here. Anyway, the train error naturally should always go down. You should not be having this spike thing there. This is nonsensical. As you increase the polynomial degree, things should not just be increasing at some point. I had a discussion yesterday about this because I didn't really pay much attention to the spike. So I was just talking to someone about how the train error is going down, but there was a spike, and I didn't pay no mind. It's just a spike, and he is well versed in the in machine learning as well. So I was like, no, this does not make sense. You can never have this. Like if you fit more and more polynomial degree, you can only get better on your training sets. You should never increase the error. So we started like thinking about, so why did this happen? So we you ran another implementation using another method instead of using the X transpose X, our what's it called, our least square solution that we specified earlier. He decided to use the NumPy function that was already provided that has taken into consideration any possible problem that you can have. And lo and behold, the train error was just going down. I did not see any spike. I was like, I know this does not make sense. Why do I have spike? And I got obsessive. It's like, why is there spike? I don't want spike. I need explanation. So I kept reading about it, and so it seems like it's because of the precision. So the method that we are using to calculate this theta has a floating point precision issue at some point, whereby the computer, I mentioned before, the floating point just explode, and then it causes this spike, and then it does not explode. So this is good to know, because it could be a good question. It's like, do you ever get to a point, like if you fit polynomial degree, as you increase the polynomial degree, does your training error ever increases? And the answer is no, because mathematically, as you increase the complexity of your model, you should always reduce your error on your training set. On your old route set, you will end up having like a larger error because of the generalization gap. But on your training set, it's always fits more and more and get better. So I hope that makes sense. I had it as a quiz in the class, but we didn't really talk about it because there was no time. Okay, great. So now we have this like wiggly thing going on in the test set, right? That we said that the generalization gap is huge because we are overfitting. So like it looks like the best solution for our energy loudness prediction, our toy task is that we should just use a linear model, right? It looks like it's like just choosing polynomial degree of 1, which is just a linear model, is the best for on the old outset. Okay, so so let's keep going. So now that we know how to do this, the next thing we talked about, so yeah, we can look at the theta, right? The theta value we talked about it in class. Again, why there are spikes as we increase the polynomial degree. So the reason why there are spikes right now is just because of the floating point precision issue based on the implementation that we used. If we change the implementation, for example, if we use a pseudo inverse, you can do that yourself, but I tested that out. It gets rid of all of the spike just by changing the implementation. It gets rid of that. At least this is what I found out so far. You know, you may be doing more research and find out that there's actually more more to it. But from my exploration and trying to understand this problem so far, I figured that if you change the, let me quickly copy this down to see if we can do that experiment together. I mean, this is a lab after all. So let's come here. We're using polyfitch, right? Let's see. So I said that if you what I tried yesterday is like I used linear algebra, and then I use P inverse instead of using solver, even though people this solver is recommended, but I'm not sure. P inverse is pseudo inverse. So, and then I did I just continue with this solution. Let's see. And then this was what I did yesterday, I think. And when I rerun the spikes suddenly disappeared. No more spike. Everything looks very natural. Spike, go. Nothing spiky anymore. This is the same equation, X transpose. Like, in fact, this is the exact equation we talked about in class. X transpose X inverse, X transpose Y. But if we change the solve, if we try to use linear solver to solve it, spike appear. We are spiky again. See, computer change its mind. Everything changed. So yeah, we have to take like a numerical course to really pin down why this is happening in the solve. Does that clarify your question? Does that make you a little bit happier? Because I was quite unsatisfied when I was trying to figure out why it was spiking. So you said, is this better? Honestly, I mean, from what my initial understanding is that it's better to use linear solver to solve this system of equation and not use inverse. So there's another function in NumPy that just compute the inverse. The inverse is always prone to some error, especially when you don't have like your X transpose X is not well conditioned. So, but pseudo inverse make it possible to still be able to compute the inverse even if you don't have a full rank. So I think pseudo inverse is good, and a lot of implementation uses it, but I cannot say that like it's better to use this approach than this approach. I don't know, because like solve is usually the most used approach. I just figured now that this is happening, and I really don't know. I cannot give recommendation on which one is better because I don't have that technical depth yet in numerical optimization problems, and what could be resulting to what. Does that just answer your question? Sorry. I don't know how to give you a recommendation because still trying to figure it out myself. Is that okay? Is that a good answer? Sorry. Okay, should we move on? Dolami is not happy. He's not saying anything. Or she. Is Dolami a she? Keep saying he. It's maybe a she. Dolami, he, she. I have to check. I'm not sure. Sorry, I have to check again if you're he or she. Oludara. Okay. Oh, they. He. Okay. Okay. I felt like I've seen you he before, but yeah. Or you've talked before and it was he. Anyway, I just don't want to assume. All right. So where were we? I mean, if you figure out that part, please do share with me. I'm always happy to learn more about these things. I love geeking out about math, as you can probably tell by now. All right, so yeah. So how do we regularize? Let's come back to regularize. We're almost at the end of the class, by the way. It's okay. Like a lot of the rest of my things here are for you to just explore. My most important goal is that you understand enough for you to be able to change things in this collab yourself and explore it a bit more. I hope this is the case. If not, I need to do better. Okay, so let's look at the polynomial regression and then the lambda here. You remember that we did solve this. We also solved it, but not in class. I kind of like gave you that as an assignment, but it's very simple. The solution for the polynomial that we gave, what did I say? Polynomial, the regularized least regression solution that we talked about in class. The solution is very related to that of the unregularized version. So it's only just have something like, let's see. So we had plus this lambda, right? Lambda high in it. This was it. So we only have this part. We lambda. I don't know. Did I miss something? Okay, so we only have this part, right? And then we still have the inverse. Please, how did you magically draw the table? Which table? Which table? I'm not sure. Is this one? I'm not sure which table. Yet, maybe. Oh, no. I mean, this one here, I just created like a text, and then we got this, and then I wrote this, and then it's starts showing on the left. I don't know if this is what you're asking. Okay. All right, thanks. So this is, I mentioned this earlier, this is just LaTeX to be able to write formulas. And I use it a lot because for work, we use LaTeX. Sorry, I said this is LaTeX. This is, it's LaTeX. We use something called overlay to write LaTeX, overlay. So if you Google it, so it's now showing my overlay. I did not want to show that before. So if you click on overlay, so overlay here, you can write LaTeX formula. You can also have it on your computer, but usually people use overlay on the web to write papers and any other thing that makes it easier for you. Okay, so yeah, in case you're just curious, this is overlay. And I also did the same for most of this slide. There I use the online version where it's called LaTeX Eats. And one thing that I found useful is like when I forget anything in LaTeX, I know what the symbol should look like, but I cannot remember how to write it. So there is something where you can draw latex and it'll tell you what the symbol should be like. It's called detextify. So let's say I wanted to lambda. I don't know what lambda is. I just draw the lambda. So it shows you option. So you can say the name is lambda. So if you want times, I don't know what it's called. So you can decide which of this are you looking for. This is times. So you can use it to learn how to write LaTeX if you're curious about LaTeX. Anyway, I like this too because sometimes I just forget what it's called. And then instead of trying to like Google the name, I just write it out, right? I'm glad you find it interesting to learn about. Okay, so let's come back to here. So this is exactly what we wrote here. We have X transpose X, right? Plus lambda. And this I here is just like np.I. Does anyone know what np.I does? Tulamo, yeah, it's like, you know, one of those things that experience teaches you, right? When you do something all the time, it just becomes like second nature to you. Like if you want to convey any piece of information, you need to be able to write it out. Identity metrics, yes, Tulamo, it's identity metrics. So if you want to create an identity, what is an identity? What is an identity metrics? So identity metrics, right? So okay, now it looks like I'm just flexing my latest skill, but it's actually just so easy to it's easier to explain it here. So let's see, do B metrics, identity metrics, right? If I can remember how to write this is in LaTeX. So identity metrics would say that I think we can have, is this correct, right? Okay, I don't know. We can have 1, 0, right? And 0, is this correct? 1. See, it looks like, oh, I'm missing something. Okay, it looks like it's all right. Let's space it out a little bit. I don't know. Maybe there's a bit better way to do this. Okay, so identity metrics just gives you 1 in the zeros on the diagonal. Is it zeros on the diagonal? Do zeros on off diagonal, channel, right? Or have I forgotten identity metrics? Should be 1 in the diagonal and zeros in off diagonal. We can check. I think this should, I mean, not I think, should be a bit strange, but don't let me boast. You know, imagine I said, I'm pretty sure this is the idea. I was like, oh shit. So that my supervisor don't collect his money again, so that you're not ready for PhD, please. Yeah, once in the gap. Just kidding. Yeah, you can see. So you have 1 in the diagonal and 0 in the off diagonal. So this is identity metrics. And you can view this like 3, right? So you just keep going 1 0 0 0 1 0, like, you know, then you have a 0, like there's probably a better way to do this thing. Okay, I haven't thought about doing this matrix. Doesn't look the nicest. 0 0 1, and then something like that. Let's space it out a bit more so it looks nice. So this is an identity matrix, right? Is that correct? Yeah, great. So so we create this identity matrix. Why? Because we want this lambda so that we can do this you know, like we can do the matrix addition together, right? Because lambda is a scalar value. It's just like one thing, maybe like lambda of 10. So you can have like on the identity, you have 10. And when you sum it with this X transpose X, it just sums only the only the each of the features, because without trying to touch the rest of the like other features that you don't care about. Anyway, this is my explanation. Like, you can go in depth if I say something that I'm not sure about. Okay, let's keep going. So we do the same thing here, and then we can have polynomial. I think we are now on time. Okay, great. This is amazing. So once we do this and we set this to 1, right? Then the problem becomes very simple. We just move from a problem that looks like what was it before? That looks like this, right? To a problem that looks like this, which is pretty cool. If you ask me, it's pretty cool, I think. And then you can keep going. Like, you know, this is like, if you won't become much more strict, you penalize it by increasing the lambda to 10, and then you do it to like 1,000. But then now it looks like you're just fitting the bias. See, you're just having this one straight line. This is not good. Anyway, so this is, you can look at the effect of like regularizing, right? So as you, like we talked about the coefficient in class, where we said that for the non-regularized weight, as you increase the order of polynomial, it keeps getting more and more, so it keeps increasing. But once you regularize it, so let's say you choose a lambda of 1 for regularization, so as you increase the order of polynomial, you know, it does not get like larger. In fact, it even gets smaller, because then a lot of the big polynomial just like end up being like close to 0, as you can see here. And the only weight that matters is around this, like less than 20, I think. I hope that explains it. Is that clear? Well, is everything clear so far? Shay, you understand what I'm trying to say so far? All right. Thanks for the feedback, Dalam. Okay, so we can do the same thing that we did before, where we computed the error, but this time around on a regularized version. And you can see now that we are no longer having this gap as we increase. See, when we increase the regularization parameter, it forces the training and the holdout set to have the same error, which is good. But as we relax our penalty, like maybe we don't do any penalty, we start having gap. All right. Okay, so this is it. I think this is the most the critical part of the tutorial. The rest, I'm just going to tell you what it is, and if you're curious, you can go do more. So in the RBF part, I was showing you how to create RBF feature, like the Gaussian, and you can play around with this. Like, you know, when you have a Gaussian with bandwidth or like the variance of 5, you know, it's bigger. If we keep going, I don't want to do much here, so because we're already over time. So this was like with variance of Gaussian of 0, like mean of 0, variance of 5. If you change it to variance of 15, you know, it's just spreads out more variance and so on. Anyway, so you can also just like plot a lot of them, like with different mean, which is what is going on here. You can now use this idea to train an RBF, which is what is here. So you're still doing linear regression, but now you have another feature, a different feature, which is the RBF feature that you got from the RBF. No, it's no longer polynomial feature. It's now the RBF. And then you can see, like, this is the fit when you use 10 of those Gaussians that we have here, when you use 10. But when you increase it to 100, it starts to overfit. And then you can also find, you can also regularize it. I did not put that here, but you can also regularize it. And I also showed you how to do k-fold cross validation, by just using the sklearn K-fold, then you can have different splits and you can just train your model, and you can see, like, visualize what the different splits looks like. And once you train your model and you get the error, you can try to see like the distribution of the error for your test and for your train. So usually when you use K-fold validation, you can just get the mean of this error would be the error that you assume for your particular setting. The mean of the test error, not the train error. Anyway, yeah, so I think this is like the rest of the slide is the rest of the notebook is just now more like asking you to think a little bit. You can ignore this part. It's just like some plus for the slides. So this one here is like what happens when we try to use more than one variable. So we've been using the energy variable, energy, just one. So what happened when we try to not go beyond energy, which gives us a mean squared error of 2.69, to add, say, danceability. So this does not seem to reduce our mean squared error. Maybe it's not a good feature, but we can keep going. We can say, no, how about we just add acoustic? Oh, 2.6, no, maybe not. Okay, maybe we can add instrumentalness. Is that a good feature for loudness? Maybe not. So we can keep going, and then, or even add more. Like nothing is stopping us. Let's add like all of this, whatever we can think of, and then use all these variables to train, and we can even create a polynomial feature of them. So we don't have to just use the for one. I mean, it's boring if we just use it. We just learned about polynomial feature, right? So we can just wrap that in like the X train that we have now, which if you look at it, it should be by 4. I think it should be as simple as just wrap it in maybe like something like this. What did we call it? Polynomial, not RBF. Polynomial feature, right? I think should be okay. Yeah, so you can just wrap this into polynomial feature. So your 10 will become this 11, and so I think now you have to reshape it, right? Reshape to be 371. So you collapse everything. So now you have 44 features. You just massively change this feature space. So like instead of fitting with your X train, you just fit with you change it. Let's see, I don't know what this will give because I've not done it before. I've not done it before this class. So 4 features, let's keep this in mind. Let's see if it's actually better. I'm curious. Now I'm curious. Let's see, X test, X train, X test, and this would be, let's do, like, I mean, it's length of this, length of X train. Oh, I think should be okay. Let's see. Surprise, surprise. It looks like we just increased our error from 2.6. Okay, maybe 10 is not good. Maybe 10 is not good. We just said that 10 was not good. Let's use 2. Let's use 2 for now. Oh, this is terrible. Okay, anyway, you see what I'm trying to do here? This is not good. So we need to think a little bit more about this. Maybe something is not right. Oh, let's use 10 and then use ridge regression instead of this. I mean, who cares, right? Ridge regression will always help us regularize it. We can just increase things. It's still 5.16. Can we get this error down somehow? Is there something missing, like going wrong in our implementation? So we now have polynomial features instead of our regular feature. But but we are still not able to, we are not doing well. When we did not have polynomial feature, we were like at 2.6. Okay, this is food for thought. So what you can try to do is like, instead of trying to predict loudness, maybe we can predict popularity. And then you can like think about this popularity column, 380, 339. Anyway, this is an not assignment right now. Like this is for you to practice. It's always good to have something to practice on. And something I was also thinking about, okay, now we really should wrap up. Something I was thinking about is that what if you want to like augment the data? So I was looking at like using Beautiful Soup because you've learned this, right? And then you can extract some artist information and their top, like, I don't know if this is legal. I just look at this site that has this chart and I was trying to extract all of the artists and the top artists, and wondering if I can use that as a feature or something. This is just me wondering how we can augment this Spotify data sets to see if we can be better, but I leave that up to you. Why everyone is laughing at me for my failed mean squared error reduction? Nah. Okay, let me know, like come to Discord if you can get it to reduce and what you did to reduce it. Life happens. I know, to the best of us, life happens. All right, no problem. I was just joking. I know you're not laughing at me. I know you're just like laughing at the fact that we were hoping to reduce and deter reduce. Okay, this is everything I have for you guys. The rest is for you to just explore and let me know what you find in this course. Just ping. Some of this is helpful for your project as well, thinking about nonlinearity and trying things out. Now that you have some understanding of the models and how to change things, I hope it makes life a bit easier. Like your knowledge, I hope that has been strengthened with this class. Okay. Without further ado, we will end the class if there are no questions. So, any question? You're very welcome, very, very welcome. Thank you for coming. Okay. Thank you so much for being here, for staying 12 minutes later. And talk later. Enjoy the rest of your week and bye.